Now we're going to look at a special logarithm function called the natural logarithm, and we're going to look at some more logarithm properties. So first we're going to introduce the natural exponential and the natural logarithm functions. We're going to use some of the exponent properties that we know to derive some properties about logarithms. And then we're going to use these properties to solve some equations. All right, so remember from an old activity, it was a compound interest problem, is suppose you had an annual interest rate of 100% and it was compounded n times per year where we let n vary to prove a point. After 1 year, you get 1 plus 1 over n to the n power, and as n gets really big, if you compound it many, many, many times, the one thing that was kind of surprising that the number did not go to infinity. It actually flattened out at a number somewhere around 2.718. And so what happens is that as n behavior, as n goes to infinity, this number goes exactly to a number called e. And again, that e is approximately 2.718, but it is actually an irrational number. And so what we call, for some reason, we call the natural exponential function f of x equals e to the x, where e is this strange number that we get by compounding our money over and over many, many times. And the natural logarithm function is going to be the inverse of the natural exponential function, log base e of x, although we don't usually write it that way. We usually write the natural logarithm function as ln of x, ln for log natural log, right? And as we sort of implied above, e is not exactly equal to 2.718, but approximately equal to it. Remember, e is actually an irrational number. And so what is the convenience about e being natural? So there are, first of all, there are natural exponential and natural logarithm operations on the calculator. So it's easy to calculate natural logarithm values more easy than, say, log base 5 values. But the question you might ask is, what the heck makes e natural? It doesn't seem very natural in our experience with numbers. Well, the answer is basically calculus. One of the things is that you learn in calculus, you'll learn an important property about f of x equal to e to the x. It is the only exponential function where the rate of change of the function is actually the same as the output of the function. In the language you will learn in calculus, once you take it, if f of x equals e to the x, f prime of x is also e to the x. And that's going to be really wild and strange, but it's also kind of a neat property of functions. And another important property about the natural log functions is when we find the rate of change of the natural log function, it'll be the reciprocal of x. And so that, again, that is something that once you've taken a bath in calculus, it'll make sense. But right now, before you've had any experience in calculus, this isn't something that is very natural to you. So basically, there are some reasons that we call them natural, but I will certainly forgive you if natural is not an adjective that you would use for the natural exponential and logarithm functions. So these are sort of things that we inherit from the calculus world, and we'll accept those, but other than that, these are no more special than any other logarithm functions that you might know. All right, so now let's go ahead and see if we can find some new and interesting logarithm functions. Logarithm properties, excuse me. And again, the way we understand logarithm everything is through the exponential functions, which we understand a lot better. So here are some exponential properties that we are going to think about. A to the m times a to the n equals a to the m plus n, and a to the m all to the n power is equal to the a to the m times n. Now, these exponential properties may not make sense to you, so let me actually give you a reason to believe in them. So first of all, let's look at that first one. Let's look at a to the m times a to the n. Now, the thing to realize about a to the m is it's just a bunch of factors of a multiplied together. In fact, m of them multiplied together. And a to the n is also a bunch of factors of a multiplied together. So in your imagination, imagine a to the m as being all these a's just multiplied next to each other. A to the n is a bunch of other a's multiplied next to each other. And when we multiply a to the m times a to the n, we put all those a's together multiplying them. And what then we need to do is to be able to count all the a's that we have in a to the m times a to the n, and hopefully we count m plus n of them. So again, so here's how we imagine it. Here's a to the m. There are m factors of a in there. Here's a to the n. There are n factors of a in there. Right? Again, the first group of a's has m factors of a. The second group has n factors of a. So if we want to count all the factors together, we just add up those a's in each group. Right? We have m plus m factors together, which means that if we look at that right-hand side as just a power of a, that's going to be a to the m plus n, which means that a to the m times a to the n is equal to a to the m plus n. We're going to use a similar analysis for a to the m to the n. Now, let's just look at that to the n power. To the n power means whatever we're taking to the n power, we multiply by itself n times. In this case, it's going to be a to the m. So what we have is a to the m times a to the m all the way to a to the m, where we do that n times. So there are n factors of a to the m, but we want to count all the individual factors of a. In each of those n factors of a to the m, we have m factors of a. So we have n factors of a to the m. Each one has m factors of a. So if we want to count all the factors of a together, we have m times a factors of a, which means that a to the m all to the n power is equal to a to the mn. Now what we're going to do is we're going to take these exponent properties and try to translate them into logarithm properties. And here's how we're going to do it. So the question we're going to ask is there a nice formula for log base a of x times y? Is there, in terms of log a, x and log a y? Well, let's see if we can find one out. So first of all, I'm going to let z1 equal log base a of x. As you've seen, it's usually easier to deal with these things when we can put them into equations. And the easiest way to put something in an equation is to define a variable in terms of it, right? So we're going to find the z1 equals log base a to the x of x, so we can play with that equation. We're going to let z2 equals log base a of y, so we can play with that equation. Nice thing is, once we have these equations, we can write these in exponential form. We can take each of these equations and in the first one solve for x, the second one solve for y, and using the inverse properties of a to the x and log base a. So the first one says if z1 is equal to log base a of x, that means x is equal to a to the z1. And the second one is if z2 is equal to log base a of y, then y equals a to the z2. And that's kind of convenient because we want to find out what log base a of x times y is. So this gives us a nice way to find x times y. Well, we just multiply a to the z1 times a to the z2. And as we've seen, this is a to the z1 plus z2. And that turns out to be a really nice form to be taking its log base a. So if we want to find log base a of x times y, that's the same as log base a of a to the z1 plus z2. But one of our properties, our inverse properties of log base a, is that if we take log base a of a to the anything, that just equals the anything in the exponent of a. So log base a of a to the b is equal to b. In this case, our b is z1 plus z2. So that tells us that log base a of x times y equals, well, if we look at the right-hand side, what we're going to end up with is z1 plus z2. The nice thing is, we know what z1 and z2 are. z1 is log base a of x, that's how we defined it. z2 is log base a of y, again, we defined it that way. So now we get the equation log base a of xy is equal to log base a of x plus log base a of y. We get a really nice equation for our log base a of xy. All right. So we have another one when we're dealing with exponents, log base a of an exponent. So if we have, say, log base a of x to the y, can we find that in terms of log base a of x or something that some other quantity that we might know? Well, let's give it a try. So I'm going to define z to be log base a of x and see if we can make any progress. Again, what I want to do is I want to flip that equation by solving for x. When we put that in exponential form, we get x equals a to the z. If z equals log base a of x, then x equals a to the z. That's how inverse functions work. So we want to find, of course, x to the y. But we already know that x is equal to a to the z. So x to the y is equal to a to the z to the y. And isn't that nice? We have a formula for a to the z to the y. That is equal to a to the zy. And now we play the exact same game we played before. If we want to find log base a of x to the y, that is the same as log base a of a to the zy. Now we can again use our inverse function trick. We know that log base a of a to the b is equal to b. If we, instead of b, we look at zy, we get log base a of a to the zy is equal to zy, and therefore that equation gets transformed into log base a of x to the y equals zy. Well, again, we know what z is. We defined it to be log base a of x. So if we plug that back in, we get log base a of x to the y is zy, and I'm actually going to write those y and the z in the opposite order just to make it look nicer. We get y times z, and again, z is log base a of x, so we get y times log base a of x. Let's go ahead and put that. And so here are our important logarithm properties. We're going to put all that together. We have log base a of x times y equals log base a of x plus log base a of y. And we have log base a of x to the y equal to y to log base a of x. And that second one's a nifty property. It says that if you take the log of anything to an exponent, that everything stays the same except that exponent comes outside the log. So let's see how this can be used to solve some equations. So in particular, 2.8 to the 3x equals 4. And once again, we are stuck in a world where that 3x is in the exponent and makes it very difficult for us to solve for x. Logarithms are going to come to our rescue, except this time we're going to do it with a natural log instead of log base 2.8, because log base 2.8 is not a nice logarithm function. It's not a function that you can find on your calculator, and so it's kind of inconvenient. So what we want to do is we want to do this with a logarithm function we can find in our calculator. We're going to do log base e, the natural log. So we're going to let a be, we're going to use our properties above to make it nicer, right? But first of all, we're going to use log base e, our natural log. And of course, we don't say log base e, we say ln. So let's call them ln. There we go. So we got ln of xy equals ln of x plus ln of y. And we have ln of x to the y equal y times ln of x. So let's go ahead and take the natural log of both sides of those equations to form a new equation. We get ln of 2.8 to the 3x equals ln of 4. And now if we compare that, the left-hand side of that equation, to our second bulleted property, that's ln of x to the y equals y times ln of x, that means we can bring that 3x down outside the ln, like so. So we get 3x times ln of 2.8 equals ln of 4, and now it's a piece of cake to solve for x. All we have to do is divide by 3, divide by ln of 2.8, and we get x equal to ln of 4 over 3 times ln of 2.8. And those are quantities that we can compute in our calculator. All right, so now I think you're ready to work on the activities. The name of the file is Logarithm Properties and Natural Logarithm.